Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 17. Basically, student, lecture number 16, we covered the architecture, detailing of the staircase, okay, and the whole architecture drawing of our staircase, okay, open wheel type staircase we are providing in our project. And you all know the project. If you starting the lectures from the beginning, so this is our project, and this is the 2D view of our project. And we are designing basically the stair for this project, okay. So yes, here we have basically we covered this whole portion, okay, and now we are in basically we covered the architecture process. Now we are designing in design process, okay. So you all know we have to calculate loads, and in loads we have to calculate dead loads. Remember that the structure drawing of the staircase is simple. It is very simple. You just need to calculate loads and then just calculate movements and then design, okay. So here we are assuming marble tiles. As you all know that on stair basically we are providing different types of materials, okay. There may be mosaic, there may be marble, there may be tiles, different tiles, okay. But here I am assuming marbles, so that by I assume the thickness of marble 1.2 inch. So you know the thickness divided by 12 times the density of that material, and the density of marble is around about 130 to 140 psf, okay, pcf, pound per cubic foot, okay. So here I am basically using, sorry, this is more than the density of concrete. I am so sorry. That is the strength, that is the density of 130 to 140 is the density of basically the mortar, I think so. That is the density of mortar, okay. So here you see the calculation, we got 0.016 ksf, okay. Remember, kips per square foot, and the density of marble is 160 at around about 2600 kg per meter square. And we need to find out the slab waist thickness, and you all know the slab waist thickness is nothing, it is just the thickness, this thickness, okay, this thickness from the this here. I basically in this drawing you will see this is around about 6 inches. Here I assume this is 6 inches, okay. This no, it show me wrong. Let me show you this thickness here. When I designing these stairs, I assume initially, no, this is not this one, okay. This is not we have to determine this thickness, okay. This is around about 6 inch I assume, but the formula is that this is the same for formula. Remember, by just using the ACI coefficient, okay, you got this one, L by 20. Remember, the stairs are assumed to be simply supported beam. Remember, although we provide here a beam, and if there is also a beam, so it depends upon the stiffness of that beam. If it is a small size beam, so then we assume that beam as a hinge support, okay, not just like a fixed support. But if it is a heavy beam and it totally basically control the movement of this flight, so then it may be assumed as fixed support, and this one as well. But although you see here we just keep the landing on the wall, so it works like a ruler support or hinge support. Clear? So this is basically modeling, how we model it, but basically we assume as a simply supported beam, okay. So that why I using L by 20, and 0.85 is the factor. Remember, as you see that there are stairs. Due to these stairs, the stiffness of the flight of the stair flight is more than as compared to RCC slab. So that why we reduce the thickness of the slab in this case for flight basically for stair flight 15%. We do the 15% reduction, and you see here. So that my L is 16.95 already we calculated, okay, in the end of lecture number 16. And you divide things, okay, you got at 0.64, and this is now my 9 inch I assume. 9 inch is my waist thickness, okay. And the effective depth is 0.75 is clear cover, and this is, I assume here that I will provide number 4 bars as a main bar. So that why there it comes, and you have to half them that bar, okay, because the effective depth is to the from from the top surface of the concrete to the center of the main bar. So here I am using 8 inch. Okay, the rest of the calculation is same. You see the weight of slab, that is 9 by 15 times 0.150. This is an inclined plane. Remember, this is a very important terminology in the design of, basically in the design of staircase. Okay, in stairs, when we calculating basically the weight of the waist of the slab of the stair flight. So basically we initially we assume that, let me show you where is the inset, this one. For example, at initial stages, let me show you here. Remember, we calculate we divide basically this is my step. Okay, this is my step. Now when we basically assume this, why not it working? Okay, this is my step, and the bottom one, this one is basically my waist slab. This is my 9 inch. This is basically 9 inch. Okay, and the rise is 7 inch, and the tread is basically 11 inch. Okay, now the weight of this stiff is basically simple. It is just you need to calculate the area of the section times the density of concrete, and the density of concrete is solid concrete. Okay, so you can use 145 or you can use 150, 140 as well. But here you have slab, waist slab. This is a rectangular portion. Okay, and remember the weight, once you determine the area, the weight of this stiff is now acting on the horizontal okay, horizontal projection. But when you using this area formula for this inclined surface, so its weights will be in this direction, inclined direction. Okay, inclined direction. To convert this inclined direction, as you see the weight is now in inclined direction, to convert them on horizontal direction, we have to multiply this weight by an angle alpha. Okay, and that alpha angle is basically nothing, it is the angle which we provide basically with the horizontal to the flight, and this angle is basically equals to t square plus r square, okay, under the root divided by t. Okay, this equals to this is basically, I think so, this is cos alpha. Okay, so this factor should be multiplied to convert that inclined load on the horizontal. This is the extra factor which we multiplied for this inclination. Okay, so you don't need to be confused in this factor. Okay, and this is some extra work, and yes, we just now it is in division. Okay, if you place that factor here, you have cos alpha. Remember, this is cos alpha. So cos alpha is what? T square plus r square under the root divided by t. So that t comes out in the nominator, and you do the calculation. This is roundabout equals to 0.844 something. Okay, so you just need to multiply, and now this is the load KSF on the horizontal surface. Okay, and remember one thing is very important, that we don't need to multiply, remember, the live load, because live load acting in this direction, but the material, the fluster which is under this waist surface is also inclined. So that's why we have to multiply the weight of plaster by this factor as well. And you see here, here we have the weight of plaster. Okay, so waist thickness is assumed 3 by 4 inch, plaster thickness is assumed divided by 12, and the density of the mortar is 130 to 140. Okay, so times density and times that factor. Okay, cos alpha factor, and you got this one. The density of plaster is 130 to 140, and the weight of the stiff, that is rise divided by 2. I already explained this. This is the density of PCC concrete. Remember, PCC. And 7 inch is the rise, you have to consider 2. Remember, average. And here I did the calculation for you people. Okay, what will be the weight of the stiff? 7 divided by 2 times 11 times 140. But ignore this 11, because we are just only calculate per square foot calculation. We do not consider this 11. Okay, we considered basically 1 feet. Okay, 1 feet length. Okay, so that's why I skip 11 inch. Okay, this is important. because we are doing calculation per square feet, remember, not 11 inch for 11 inch. Okay, so 0.042, and these are some extra information for you people, how much the density of different material. Now the total dead load, just you need to add all the loads, you got 0.16 kSF. Live load, this is important. For staircase design, we assume live load from 150 to 300 kg per meter square, and this is 30 psf to 60 psf. I am using 60 psf, it's equals to this one. I need to factor the load, and this factor load will be acting in the case of first and my second flight, 0.288. Now remember, this load will be on this flight and this flight, so we just only design this flight. Okay, and now we start basically loading up landing. Yes, this is important, that here we have landing. Okay, so on landing, basically this is horizontal surface, so that's why we have to skip that factors. Okay, so if we skip those factors, so waste, or you can say the slab weight, now no need of factor, because that is a horizontal surface. Remember, here we have to use that factor, but the landing is totally horizontal, so that's why we skip that factor. The marble weight will be same, fluster weight will be same, but we have to skip the factor. Okay, and then we add up things. We got dead load is this much and live load is this much, and the same live load. Now WU for load landing is 0.26. this is a little bit smaller value. Okay, now two options. We have to go further. We have two options. Either we design flight as a beam by just considering the width of the beam is 6 feet, or either we can design the flight as a strip. Remember, this is very important. This is very important. Okay, that as you see here, this flight, basically you can either design this flight as a beam. Okay, as a beam, you considering the total this total flight as a beam. Remember, as a beam, by just considering its length and its width and its depth. Its depth is how much? Its depth is basically, you see that the depth is 9 inch, the width is 72 or 6 feet, and you just consider 1 feet length. Okay, as we design basically a beam, just like a beam, or either you can consider one strip of this flight, and you just design for that one strip as we did in for slab. Okay, so here you choose like a one-way slab design. Okay, in that case you just need to consider 1 feet strip. Okay, so you have two options, and I'm using that. I suppose that I am doing the calculation as a beam. Clear? So here we have, okay, we consider this hole as a beam, remember, and we just consider 1 feet length and 6 feet width. Okay, and this is flight 1, and that is landing. Okay, its thickness, the thickness of the beam or the depth of the beam is 9 inch, and the effective depth is 8 inch. Okay, and like a beam, like a horizontal beam. Remember, we consider this inclined as a horizontal beam, and this length, okay, 10.558 feet, and this length will be 6 feet. And yes, so you see WF1. Now remember, this is important. We calculate this load for flight 1 is 0.288 kip per square feet. If we are designing as a beam, then we have to convert this square feet loading in per feet. So for that purpose, we need what? We have to multiply them with a width. So that gives us 1.728 kip per feet. And similarly for landing. Okay, so for landing, and the width will be 72 inches, and this thing is very important. This information is very important. Clear? That now when landing comes under two flights, like in case of quarter stair, then landing supports, remember, this is very important terminology, and which I want to share with you, that let me show you here. Okay, remember, this is the flight and this is the landing. and this is again the flight. So whenever you found that landing comes under two flights, basically in this case this is called quarter type landing, so quarter type stairs. So here basically the landing act like a two-way slab. Remember, it works like a two-way slab. It distributes loads basically in two directions. So that why you see the loading will be less on the landing and maximum on the flight. So here we consider the total loading on the landing, we divide that by 2. And basically this means we consider 50% load of the total load. Okay, we half that load because they are distributing in two directions, as we did in basically in calculation in two-way slab analysis. Okay, so this is very important point. This is very important point. Okay, you must consider this. Okay, and that's why you see here where is the, this is page number 9, this one. Okay, loading on the landing, you see WUL denoted, this is 0.2604 is calculated, but the width of the landing is 6 feet, or you can say the length, and WUL is 6 times 1/2. We consider half loading now. Okay, so that was 0.7812 kip per feet. Now what you need to draw the beam right now. Okay, so the beam is drawn here. You see ruler support and hinge support. This is flight, this is landing. Clear? The landing width length is 6 feet and loading is now recalculated 0.7812 kip per feet, and 1.7 is already calculated on page number 7, sorry. And you just need to analyze this beam like a simply supported beam. Okay, here you see R1 is calculated, total loading, okay, divide by, just I take moment here and I use the moment equation and I got 9.67. Okay, 9.67 and 13.20, you see here 13.29. This is R2 and this is R1. Now you need to draw the shear force diagram. Okay, this is shear force diagram. Due to this load it will be inclined and further inclined. What you have to determine that point at how much distance it will be from the support, or either from this point, that where your shear becomes 0, and this is X. Okay, I denoted that distance from this, let's say this is X, and 10 minus this is okay. And now you see this is first degree line. So these are similar triangle because one angle is combined, or you can say this is you can say the combined angle of these two triangles. So that's why it is these triangles are relative. So we will using the similar triangular rule. Okay, X divided by 4.98 and this 10 minus X divided by this. Okay, and you got this.